We have learnt about how it is possible to sample the spectrum which is obtained by taking the discrete time Fourier transform of a signal called as x of n. X of n is a discrete time sequence. It is said to be aperiodic. Hence, we compute the spectrum by obtaining the discrete time Fourier transform. The expression for discrete time Fourier transform is shown here. We obtain the spectrum which is called as x of omega, and omega is said to be between 0 to 2 pi and it is periodic. Hence, to make it more computationally efficient, we decide to sample the spectrum which was periodic as well as continuous. The process has been described. The omega is changed to omega k is equal to 2 pi k by n, and the condition we have learned is that we have to avoid aliasing in the time domain. So we considered a periodic sequence called as xp of n, which is derived from x of n. Now, in order to obtain x of n from xp of n, the condition to be satisfied is there should not be aliasing in xp of n. That is possible by taking the value of capital N to be greater than or equal to L, where L is the number of data points in x of n, and n is the repetition interval which is defined to obtain xp of n from x of n. So after the process of sampling, we obtained what is called as x of 2 pi k by n, which is equal to summation n between 0 to L minus 1 x of n into e power of minus j2 pi kn divided by capital N. Now this equation in the LHS could be written in a more concise way as x of k. K here represents the index, and the index is an integer which lies between 0 to n minus 1. On the RHS, we can increase the length of x of n to the value which is called as n. This is possible by not changing the sequence, by simply appending sufficient number of zeros, and this step is called as zero padding. Zero padding is a method to increase the length of x of n by appending appropriate number of zeros. So an L point sequence will now become an n point sequence. Hence, the equation above can now be represented as shown here. And this particular equation is referred to as the discrete Fourier transform. It happens to be a discretized or a sampled version of the discrete time Fourier transform. Let us now discuss about the DFT, which can be used as a linear transformation. First, let us consider the equation called as the DFT. The DFT of x of n is denoted as x of k and is given by the summation as shown. The summation is having the limits n from 0 to n minus 1. The inputs are x of n, which is the time domain sequence. This input x of n is multiplied by w of n, which is called as the twiddle factor, and the twiddle factor has a power which is equal to kn. The result of this applying DFT on the time domain sequence gives you the frequency domain sequence called as x of k. The range for k is between 0 to n minus 1. So this particular equation is referred to as the n-point DFT. Similarly, the inverse transformation is referred to as the IDFT. The IDFT is performed on the input, which is called as x of k. So x of k is a frequency domain sequence. Taking its IDFT gives you the value called as x of n, which is a time domain sequence. The expression for IDFT is 1 by n times summation with the limits k from 0 to n minus 1. The input is the frequency domain sequence x of k multiplied with the twiddle factor wn with the power minus of kn. Here the value of n lies between 0 to n minus 1. Therefore, from the above two equations, which look similar in some ways, we can draw some conclusions. First, the computation of each point of the DFT, it requires n complex multiplications. The input x of n in general could be complex. Wn, which is represented as e power of minus j2 pi by n, is a complex exponent. Wn is called as the twiddle factor, also referred to as the phase factor. The amplitude here happens to be 1 and the phase you can observe is given by minus 2 pi by n. Since you are multiplying x of n, which is complex, with another complex number which is called as Wn to the power of kn, this can be treated as one multiplication. The expansion of this summation will give you terms which has n ranging from 0 to n minus 1. That is capital N terms in total. So each term involves one multiplication. Therefore, there are n complex multiplications. Now, in between these n multiplications, we will have n minus 1 addition operations also. Each addition will be between the two product terms. So if you count in this expansion of the summation, the total number of complex additions are n minus 1. Next, the entire operation of calculating the DFT is done for k value between 0 to n minus 1. Therefore, to get the n individual answers, this process has to be carried out n times. For a single term, we discussed that there are n complex multiplication. Therefore, for n terms in total in x of k or x of n, we have to perform this operation n times. So multiplying it by n into n, the total number of complex multiplications an n-point DFT requires is given as n square. And the total number of complex additions, since the operation is done n times for n different values, therefore it becomes n multiplied by n minus 1. This is an important result which you have to remember. The total number of complex multiplications in DFT and IDFT is said to be n square. The total number of complex additions involved is said to be n into n minus 1. Now let us discuss about the DFT and IDFT, which can be viewed as a linear transformation on the sequence x of n and x of k respectively. First, let us define an n-point input vector which is called as x of n. So here I use the small x to denote the input term and we'll use the capital X to denote the output term. Since each vector is of length n, therefore the subscript letter is called as capital N, which denotes the length. So we have an n point input vector, which is small x of n, and we have an n point output vector, which is denoted as capital X of n. The twiddle factor matrix W of n is said to be an n cross n matrix. Therefore, if we represent the two matrices in a column fashion, then we have the column vector small x of n, which is the input vector. The input terms are x of 0, x of 1, x of 2, and so on. The last term will be x of n minus 1. Similarly, the output term capital X of n will be capital X of 0, x of 1, so on till capital X of n minus 1. Therefore, if we want to write down the dimensions of this matrix, it is comprising of n rows and it has a single column, or it can be called as a column vector. Now, coming to the twiddle factor matrix, W of n is treated to be an n cross n vector. To arrive at the values of this n cross n, we take the value W of n for a certain number of points called as n. This W of n is common throughout the whole matrix. The power of W of n is decided based on the row number and the column number. So the first row is numbered as 0. So you can see in the first place, for each element in the first row, you will have a value which is identical, which is 0. The row number is common, but the column number, it changes. First column has number 0, second column has 1, then 2, and so on. The last term will have a column number n minus 1. Coming to the second row, the row number now becomes 1. So first row had row number 0, second row will have row number 1, corresponding column numbers are applied. This process continues. The last row will have a row number n minus 1, the column numbers respectively 0, 1, and so on till the last term n minus 1. Now, we observe that since when you simplify, the result of simplification would be something like this. The first row and the first column has powers which is 0, and any term with the power 0, we know the answer is going to be 1. Therefore, first row and first column in twiddle factor matrix is comprising of values which is 1s. The second row we can observe has powers which are multiples of 1s. So the powers are 0, 1, 2, and so on. The last term is n minus 1. The third row will have powers which are multiples of 2. Next, we'll have multiples of 3, and so on. This is how you can remember the pattern in the twiddle factor matrix. Now, performing simplification, as we discussed, the first row and the first column will be made equal to 1s. The remaining powers are illustrated here as we had discussed. So here we have twiddle factors, W of n, which are powers of, they are multiples of 1s. Next, you will have multiples of 2s. Next, you will have multiples of 3, and so on. The last row will have multiples of n minus 1. Using these notations that we just described, the n-point DFT can be written in the matrix form as follows. The expression for the DFT becomes capital X of n, which is the output vector, which is a column vector, W of n, the twiddle factor matrix, which is n cross n, x of n, small x of n, which is a column vector with n elements in it. This is the method of describing a DFT. Is it possible to represent the input and output small x of n and capital X of n in the form of row. Yes, you can do that. But when you do that, the position of the input will be placed first before the triple factor. We have to remember that we have to satisfy the rules of matrix multiplication. So if at all we are going for multiplication, the inner dimensions here, the inner dimension for the first matrix, inner dimension is going to be capital N. For second matrix, inner dimension is n. So since it is matching, we can go with the process of multiplication. But if at all we place x of n first, it cannot be in the form of a column, because then the inner dimension will be 1 and here you will get n. So matrix multiplication will not be possible. Therefore, if x of n comes first, it should be in the form of a row. And correspondingly, the answer you will get will also be a row matrix. So the rules of matrix multiplication have to be remembered. Now, can we have the inverse of this? Yes. To compute x of n, w of n has to be taken to the other side, and it becomes wn to the power of -1. Now, since w of n is a symmetric matrix, we assume that an inverse exists, then the IDFT formula can be expressed in matrix form as x of n equals 1 by n times wn star, where wn star is called as the complex conjugate of w of n. So we have found what is the inverse for w of n. Let us now multiply it with capital X of n, which is the frequency domain representation of the sequence. And this yields the time domain representation called as x of n. So this particular expression is called as the IDFT expression. Once again, the equation for DFT is capital X of n equals W of n, which is n cross n, multiplied with x of n, which is a column with n elements in it. So the number of rows is n, the number of columns is 1. Similarly, the IDFT equation, small x of n, the time domain sequence, is equal to 1 by n, n being the number of points of the DFT, multiplied with wn star, which is complex conjugate of w of n, into x of n. Capital X of n denotes the frequency domain sequence. This is an n point column vector, and w of n conjugate is an n cross n vector. The result you get, x of n, is also a column vector. Thank you all.